Hi, everyone. Jacob and I are here to talk to you about the macOS Endpoint Security Framework. And depending on how you feel about macOS logs, either you can think of this in a happy tone, like, oh boy, not another macOS log source, or a sad tone, like, ah, oh, not another macOS log source. Anyway, before we get into things, we're going to introduce ourselves.
Hi, everyone. I'm Jacob Latonis. I am currently a staff software engineer on the threat research team at Proofpoint. So I'm building out tooling for threat researchers most of my days. As for the macOS world, I've been in it for about 2 years. I worked on all of the YaraX Mach-O module parsing. So I've been knee deep in Apple documentation and Mach-O header stuff for the better part of a year. If you also have to interact with Apple documentation that much, I feel your pain and I'm sorry. But yeah.
Yep, and I'm Julia. I'm currently a software engineer in GreyNoise, but in my past, I participated in DFIR from a consultant perspective, as well as a software engineer for internal tools. And during that time, I always really liked the macOS cases because, at least from my perspective, they always felt more intimate, like you were working with 1 or 2 devices usually, and we just didn't get to see them very often, so they were always a lot of fun. Okay, so before we get started, I just want to set some baseline assumptions for the scenarios that we're going to talk about and the scenarios for which we think this will be helpful for you. First, we're going to assume that there's currently an ongoing incident, or the events that you want to look at happened fairly recently, like in the last few days or so. We're also going to assume that you want an understanding of some lower level system events, so like file open, file create, process creation, process execution, stuff like that. And then we're also going to assume that you're maybe performing a threat hunt. Maybe you're in a sandbox environment and you want to look at what malware that's being executed on that system is doing at a lower level. Okay, I also want to put this in a higher level cultural perspective, you could say. I'm sure you are all aware that this is not true, but there is this very pervasive myth that macOS devices are just inherently safer. This is for one reason why this is a thing is that there was this very aggressive marketing campaign by Apple that started 2 decades ago, where you'll probably remember this commercial where a macOS device was framed as this healthy person, and then Windows PCs were this sickly guy coughing a lot. So after that, that marketing campaign started, this myth has kind of continued to be a thing, I think, amongst the general populace, but we're a little more technical. We understand that macOS malware is a thing and it affects devices that maybe we just don't work with them as much. They don't have the market share that PCs do.
Yeah, and if you have been in the Mac OS landscape for the past year or so, you're probably seeing that it's getting busier, right? There's more things in it. There's nation state malware, there's commodity malware. Script kiddies are still trying to target Mac as well with OSA script and some other stuff. But we feel like we need to bring this back up, that the macOS landscape has always been here, but it's definitely getting louder. It's getting busier. More startups, more companies are using macOS more so than Windows or other enterprise things. And we're seeing weird things, right? You're seeing malware written in NIM, Rust, Zig, all of these weird languages that you used to only see on Windows for people that wanted to get hardcore. It's now on Mac too. All of these things that you're seeing on Windows they're coming to Mac. The landscape is growing. So best time to talk about it is now.
Cool. Okay, so now that we have kind of the high level context for this stuff, I want to talk about what typically goes into a macOS investigation from a log perspective, so that you can better understand what role endpoint security would play. Okay, so the first one I want to talk about is sysdiagnose. So sysdiagnose was mainly a diagnostics tool that was created primarily for macOS developers that were looking at bug reports. So they wanted to understand what is happening on my system in the last minute or so. So it runs a bunch of diagnostics tools, and that is going to contain information about running processes, installed applications, system events, all sorts of diagnostics tools that you can imagine, and then it puts that output into a gzip, basically. And so the way that you can collect those is with sudo sysdiagnose. If you go to the next slide, we have a screenshot of the man page for sysdiagnose. So it's a few more details about exactly what information you're getting. So recent crash reports, disk usage information, and then you're also going to get recent system logs. So that brings me to the next tool. And this one is called log. So log is another built-in command line tool for managing and investigating and collecting system logs. So log can be used to pipe the log events to the terminal, but where it really shines is you can use predicate-based filtering to get exactly the log events that you want. So if you have a Mac in front of you and you open up a terminal and you run log show, you're going to be inundated with just a bajillion events that are happening on your system. But if you use predicates, you can filter those down into what you really want to drill into.
And then next, we're going to get into the Apple Unified Log, which if you've done any incident response or investigations on Mac lately, you'll know that there used to be a whole lot of like disparate log sources that you had to like hunt around on the Mac and like find and synthesize all of your findings from that. The Apple Unified Log is Apple's attempt to unify that like logging ecosystem into like one solid place that you can then use tools like the log command or other things to view that data and have it all in one place. So one thing to note as well is while system binaries are logging to that, if you have like an application that is not from the system, someone developed it, they can actually log to the Apple Unified Log too. So you will also see user events and things if those applications log there. But yeah, so the logs are viewable via the console app as well if you've ever looked at that on the Mac. And there's a slew of information. There's system logons, there's sudo commands, there's DNS resolutions, there's gatekeeper events. If you're not familiar with gatekeeper, like when you download an app off of like GitHub or something and it like whines at you and it's like, hey, don't run this. This is from like an unidentified source. And then you say, I don't care, I'm not going to read that. And you click allow anyway. That's gatekeeper. And then Xprotect is another one where it's like if you download something that Apple deems malicious in the past or like something like that, it's basically just Yara. But it will also move those to the trash and you'll get those events. And if you've done a case with any like Apple stealers lately, like Atomic Stealer or anything like that, you will have seen the AppleScript activity in the logs. I'm sorry if you have, but there's a whole lot more to look at and we're also going to dive into it later.
Yeah, so if we put those last 3 slides together, Apple Unified Log can be collected with log, and then you can also collect a snippet of them with sysdiagnose. So that's kind of how they come together. The last one I want to talk about is FS Events D. So FS Events D is a process that monitors file system changes. So it monitors like file creation, file rename, moving a file, changing the permissions on a file. And these events are contained within a bunch of these little files within this .fs events D folder. The thing to remember about FS Events D is that you unfortunately don't get those granular timestamps that we really like. You can sort of guess within like a day granularity of when something happened, but the only thing that you can for sure glean from this is that, okay, this happened on this system. The other thing to note is that if you update the OS, this folder is going to get wiped, and then there have been some observations of some file system events just not being recorded by FS Events D.
And now we get to talk about what was in the title, the Endpoint Security Framework. It's an API that is a C API that was released in 2019, and it provides visibility into like lower level system events like we mentioned earlier. So file opens, process execution, system calls, and like 80 other types. We don't have the time to dive into all of them, but we will talk about the ones that we think will bring the most value. And then the other thing that we're going to mention, because I really just want to talk about it later, so I'm going to talk about it now so you're ready, is that starting in 15.4, modifications to the TCC database was added into endpoint security. So the little pop-ups like you see on the left, that's part of TCC, and those events are now there where they used to be somewhere else. That was kind of a mess. And then one thing to note with endpoint security is that all of these events are streamed. They're not logged by default. So like your EDR might be logging them when they hook into the endpoint security framework, but they're not logged by default. They're solely streamed. So if you want to be able to leverage these, we have to have a tool we'll talk about that collects these and types them either into the unified log or to a file, something else. But yeah.
Okay, so first I want to get into like the sorts of events that you're going to get from endpoint security, and this is by no means a complete view, but these are just some that we think are relevant to a typical investigation. So you have exec, that's going to indicate the creation of a process, and then you also have file system events. So you'll get open, which is the opening of a file, create, which indicates that a file was created on the system, and then you also get unlink, and unlink indicates the deletion of a file. And then we'll also talk about a few more. So U times will indicate that a file's access time or modification time has been changed. Like Jacob mentioned, there's also this TCC modify event, which indicates that there's been a modification made to the TCC database. UIPC connect means that there's been a connection made over a socket. And then BTM launch item add indicates that there's been a launch item or background task created.
Cool. And with all of these event types, we get relevant data in those. And some of them have data that is accessible in most, if not all of those events. One of those is the ES process struct. So in the process struct, we get quite a bit of data. We're going to point out some of the ones that are most valuable to look at right away. So the executable struct is basically it contains executable file path and metadata about the executable that like made that thing happen on the system. And then next we have is platform binary. So this is a quick way to check if the binary is signed via Apple signatures or if it's signed at all or things like that. And then we do have a start time timestamp, which is for when the process that did the thing that the event happened, when that was actually forked by the system. And if we dive further into the process struct, we're going to get a lot of cool things to mention. So we get the parent ID, which is PPID, and then we also get the original PPID. So on Mac, processes can actually be reparented if the parent is closed or it dies before the child process. So to avoid having an orphaned child process, macOS will actually reparent that. And it keeps track of that, so that way if you're ever having to build things out or look for correlation or anything like that, you actually get the original PID and then the PID of when the process ended. We also have group ID, so if there's a group of processes, you will be able to also correlate via that. And then there's also the process session ID, which you can track. And then finally at the bottom, we get the audit tokens. So one thing to note about macOS is parent ID is not always like how you think about it like on Windows. It's not always the process that made the other thing happen. So it is like, there is a parent ID of a process that it is its parent, but it's not always the responsible thing to happen. So because of how Mac routes some process creation and things, you might see that the parent PID is 1, even though it's much later on. That's just because of like the launch daemon or something like that, routing it to be started that way. And to combat that, we have what's called the responsible audit token in these structs. And that is saying this process is responsible for starting this process or causing it. And we'll refer to that as RPID in all of the future slides. And with that, you get the information of like how you can build out process chain, hierarchy. It's actually really useful. Parent PID can still be useful. So this is by no means us saying ignore the parent PID. Sometimes it is how you expect it to be on Windows. Sometimes it's not. You just have to pay attention. What's responsible for what and really.
Okay, so how do you collect these events? Like Jacob mentioned before, this is not something that's by default collected on your system. So you actually have to take some proactive steps to make sure that you have access to these events. And the way that we're going to talk about is with this built-in command line tool called ESLogger. So ESLogger can be used to emit endpoint security events to standard out. They're emitted in JSON-L format. Or you can also use the --os log option to emit them to the unified logging system. So if you call back to what we were talking about before, you can use log or the console app to view those logs. And then with OS log, the endpoint security events are going to be piped to that system. The thing to remember about ESLogger, you have to run it with sudo. And then the first time that you run it on your system, you have to give terminal or whatever you're using to run ESLogger full disk access. So you'll get a pop-up. So we have an example on the left. We'll run sudo ESLogger, and then we're going to pass the event types that we care about. So we'll pass exec, fork, and exit. So in this example, we just care about like the process lifecycle, and that's going to subscribe to exec, fork, and exit events, and then append them to this temp file. The other thing to note about ESLogger is that it doesn't support auth events, and there are some fields that are unavailable. Won't go into it. It's in the Apple documentation.
So now we're going to look at the actual like event types, and then we're also going to have code on the left that you like would cause those type of. So it's not the only type of it's not the only piece of code that would cause these events, but it's good context for you to see what malware may be doing it or how these are caused on a system. So on the left, what we have is we have a method that pretty much establishes persistence on a macOS system. So we have a plist in memory that we then write to a location. So you'll see on that F close, that's basically saying flush this to disk. We're going to write it. And we have the create event in the top right, which is we have a timestamp, we have a PID, we have a parent PID, which in this case is useful to us. It's not one, it wasn't spawned through like that. We have the RPID, like we mentioned before. And then we also have the executable path and then the file path. So executable path would be from that process struct we showed earlier that like is the binary that caused this event to happen. And then we have file path, which is the actual file that was written to disk. And then you'll notice here at the bottom left of the code block that we're also calling a command via that system function. So what we're doing is we're trying to use launch control to load this plist to always have it launch like this for persistence when it starts.
Okay, before I talk about this, can you tell everyone how we got the snippet on the right? I think that's important with your Python script.
So one thing, yeah, that's a very good point. One thing to note is after this talk is over, we will publish on GitHub we wrote a little parser. So you can either pipe it to the Python script or you can pipe it to a JSON-L file and get those logs. And then we parse them out to get the relevant info. So by no means is it like a super serious hardened, like ready for production script, but it does give you some like inspiration on what you can draw from it and the things you can extract. It's very extensible. We have functions for each type of like event type and all of those things that we talk about here today in the slides. If you want to like extend it to do other event types, you can.
Okay, cool. So this next example is that unlink event that I mentioned earlier. So on the left, we have a C program that gets its own path, and then it passes that to this unlink function. So essentially what it's doing is it's deleting itself from memory, but that process remains, deleting itself from disk, but that process remains in memory. So the way that that would show up in our parser output is you have the executable path that's responsible for that action. So it's this delete me program. And then you have the file path that's like the subject of the action. So it's the file being deleted. So in this case, you'll find that they're the same path.
One thing also is we have all of the code examples in the repo as well. So if you want to play around with it, or see these events on your system, you can as well. Next, we're going to go over the open event. So this is like anytime a file is open for any reason. This level of visibility can also get very noisy. So I just want to start out by saying, if you're looking for open events and you're not doing any of that predicate filtering like Julia mentioned earlier or anything like that, this can get pretty loud pretty quickly. So just be careful of that. Make sure that you are monitoring directories that you care about and all of that good stuff. But as you can see, we have an F open. That's just how you open a file in C. We have the executable path again, like we mentioned. This one happens to be named Chrome update and is a binary from the user's download folder. That's probably not legit. That could be something to look into in of itself. But we can see from the file path that we're opening a file in the user's home directory called .wallet. Is this trying to steal your like crypto credentials? Could be. But this is the kind of things that you can extract and be able to build out that you wouldn't see from just normal like process exec or things.
Okay, and now I want to talk about this thing that we've been alluding to in the last several slides. So TCC stands for Transparency, Consent, and Control. It's the mechanism by which macOS keeps track of the permissions that certain binaries on the system have to system resources. So like Jacob mentioned before, the TCC modify event is going to indicate that there was a modification made to the TCC database. And that database is the data store by which your system keeps track of these permissions. So the way that this works is when an application attempts to access some system resource like your camera or your accessibility features, that request is going to be routed through the TCCD process. That process, it's going to see whether it's the first time executing this program, and if it is, it will prompt the user to grant the permissions that it needs. If not, then it's going to check the TCC database for those permissions. So that's kind of how this works.
And as you can see on screen, we have an example TCC modify event to go into. One thing you'll notice that there's a little bit of different information from the other events that we've been looking at. We have this instigator field, which is basically the thing that the user granted the way that the user granted the permission to allow, deny, what have you. And one thing to note, which is interesting when you get into macOS stuff, if you ever see the instigator being this security privacy extension, that means that the user clicked allow or deny through the privacy, like the system settings window. It used to be called system preferences. I still think it should be. I just want to throw that out there for anybody.
All right.
But if you see that instigator, you'll know that the user clicked it and did it themselves. As always, we have the PID. In this one, we have the example of the parent PID being 1 because the TCCD process was spawned like at start. So it's not the parent PID that you would expect. But we have that responsible PID being 149. So we could look back in our process hierarchy and be able to relate those, as well as the executable path is TCCD. That is because of what Julia just mentioned earlier about the routing process of looking for the permission. We have the service, which would be accessibility. So this is like, having full control over being able to see your screen, the things you type, et cetera, in which normal, like non-malicious binaries would be able to assist a user in like keyboard shortcuts or something like that. And then we have this write details object. One thing to note, this looks pretty and like all the strings like say allowed and things like that in the service type because the parser has track of the enums. When you look at this in the like endpoint security logs, what you see is like the enum value. So it might be an integer, from 1 to 137, something in there. But the parser has those in there to make it readable for you. If you just want to see those and not have to read the Apple docs, it's in there for you to take out. But in this example, we have authorization equals allowed, and then we have the bundle identifier for terminal, com.apple.terminal. And finally, I alleged to it earlier, or I hinted at it earlier that I only wanted to talk about TCC just so I could bring this up. So the TCC database is technically owned and readable, writable by the current user. I say technically because it's kind of weird. If you want to read the TCC database nowadays, you have to, 1, have sudo, and 2, whatever you're using to read it has to have full disk access. And it's writable, but not in the way that you might expect. So nowadays, directly modifying the database is protected by system integrity protection, otherwise known as SIP. So that's basically Apple's way of protecting things that they don't want you to modify. If you want to modify things behind SIP, you have to like reboot into recovery, disable SIP, modify it. Or if you want like a better window manager that isn't the standard Mac one, you can also turn off SIP, but then you have to leave it off. Not that I would ever advise anyone do that, but you can be really productive when you get away from the Apple window management system. All right. Legally, don't turn off SIP. But if the executable that wants to write to the TCC database has the entitlement granted to it to write to it, then SIP allows it and it says, okay, you're good, I'll let you write to it. But back in the day, you could technically write to the database yourself before it was protected by SIP. So it was just readable, writable by a standard user. No sudo, no anything like SIP. And a company that manages files and backups and all of those good things actually used to just modify the database themselves because they didn't think the user could like give them permission to manage your accessibility features on your Mac. They would actually just on install run a little script that opens up a SQLite shell and then inject themselves into the database. Back in the day, this was also how threat actors used to like bypass TCC. So if you had any detections and you were like running Dropbox in like an enterprise environment, it was probably blown up pretty loudly. When this was found out and revealed, they actually like went on the forum post and they're like, oh my God, I'm so sorry, we won't do it again, and then just kept it. They've changed now. They now ask you for your permissions because they have to because of SIP. But back in the day, it was easier to just assume that you were fine with Dropbox controlling your entire system.
That was so nice of them.
Yeah,
Why'd they stop?
The internet got really angry.
Yeah. Okay. So like we mentioned before, there are proactive steps that you need to take in order to get access to the endpoint security data. So how can you leverage it in an investigation? ESLogger, like we talked about, is really helpful, and it's really not difficult to take that information and put it in a form that's readable and usable by you as an investigator. So a simple Python script, like Jacob mentioned, or even piping that output to JQ is really all you need. And with a Python script, for example, you can put that data into like a SQLite database, right? Something that you're used to working with. The other thing to note is that EDRs, the way that they get telemetry for macOS devices is through endpoint security. And so if you have access to any sorts of configuration on an EDR, you want to make sure that the events that you care about are being parsed out and collected if possible. The other thing I want to mention is Jacob mentioned that this is a C API. And if you read the documentation, it's technically like the most preferred way, the most complete way to listen to events from endpoint security. But it's just not really feasible because the binary that listens for those events and that leverages the endpoint security API needs to be both signed and notarized by Apple. And that requires a developer account, which I believe costs some money.
It does.
And it takes some time for that to happen. So it's just not really feasible if you need something now. So that's just a little side note.
It's very similar to the system that Microsoft does for like kernel drivers, if you're familiar. Like there's an extensive review process to make sure you're not a threat actor.
But ES Logger is complete enough for realistically what you're going to need.
Cool. And there's a lot of documentation by Apple, by others. We don't want to direct you just to the Apple documentation because it's a little scary and also like it's kind of bad. But basically, we have things that are actually, we think that can get you up and running really quickly with ES Logger and being able to test this out on your own systems. So there's an article called Blue Teaming on macOS with ES Logger by Cybereason. They get up to speed really quickly with like, these are what the event types are. This is what you can monitor for. This is why they might be triggered. It's not all encompassing, but there are events on there that you can do. Second is an article published by Huntress called Endpoint Security in a macOS World. If you're not familiar with Huntress, they have a really smart macOS team. Two of my really good friends, Stuart and Alden, are on that team, and they bring out really good macOS content all the time. It'll get you up to speed pretty quickly. If you are curious about hearing about all of the macOS stealers that I've said like 7 times already in this presentation, they cover a lot of them in a lot of good depth. So if you want to see that weird OSA script or Apple script stuff, it's there. Next up is TCCing is Believing, which was written by Patrick Wardle over at Objective-C. This gets into the nitty-gritty of why TCC should be in the Endpoint Security Framework, and he wrote this very large blog post that goes very in depth on like how this is beneficial and how TCC is for the better because of it. Finally, we also have Threat Hunting PIDs with Apple's Endpoint Security API, written by Jaron Bradley. He's over at Jamf. His personal blog is The Mitten Mac. This one goes into, earlier I mentioned like the responsible PIDs versus parent PIDs versus like the reparenting process and all of that good stuff. If you want to see like how you can build out correlations and track these things instead of just like parent PID, this is the article to do it. It will get you up to speed pretty quickly. There's some cool tools to like help you visualize these things. There's also so many more and so many more resources that you can view, but these will get you up to speed.
Yeah, I think a lot of those also, they're more from like a detection engineering perspective. From a DFIR perspective, because you have to take those steps to get access to that data, you just have to know that it's there and take the steps that you need. Yeah, I think as DFIR professionals, we just need to know that something is there and that we can do something about it. Okay, and lastly, did anyone clock that these were HyperCard slides? Thanks, Colin. Thanks, Will. Yeah, so I kind of just decided to take this as an excuse to learn a little more about HyperCard. HyperCard is a hypermedia editor that was bundled with Apple computers in the mid-'80s, and it's a lot of fun. From what I've heard, it's a lot of people's like first foray into programming because it supports HyperTalk, which is a little programming language for doing things with HyperCard. So it's a lot of fun. If you're interested, I would recommend looking into it. It's really cool.
You want to tell everyone how you wrote them in an emulator from like macOS 7?
Yeah, so there is a HyperCard like web simulator that you can play around with, but I was scared that those slides were like going to get lost into the ether, and so I just emulated macOS 7.5.6 on my MacBook Air, and then ran HyperCard on there. And if you like look into this, there's like 2 guys on the internet that just like respond to all the forums about like old macOS stuff. And like they're putting in work. It was great. It was really helpful.
And I think we have time for questions. We'll only accept the easy ones. If you have any difficult questions, I don't want to hear them.
Phil can take them and answer them.